Good morning. So actually I thought we'd dip a little bit into one of the main themes I think that will be coming up over and over again over the next day and tomorrow as well if you're staying for both days, which is going beyond just kind of the multi-core and many-core and really getting into heterogeneous computing and what the major trends are there and how that's going to affect all of us and the kinds of programming models and software development that we're all going to have to be doing. So just a quick bit of motivation first. As a computer architect, you've always got to start with Moore's law. So here's the modern day take on Moore's law, which is taken from the International Technology Roadmap for Semiconductors. And it's a very complicated slide that basically says we're going to keep getting more and more transistors. And just to kind of make this slightly easier to understand, here's a cartoon version of this graph. And basically the Moore's law we're all used to is twice as many transistors every 2 years. That's kind of what we've all become very used to expecting. And recently we have been tracking this curve, so both high-end processors like a big server chip, or even in the lower-end processors, the embedded space, we've been tracking this curve, and right now a big chip is kind of 6 to 7 billion transistors, which is a phenomenal number. But even in the smaller and more embedded chips, we're getting up to 1-2 billion transistors, that kind of order, which is a heck of a lot of silicon real estate that we've got to put to good use. So this is one of the main drivers behind why we're getting more and more cores and why they're becoming increasingly heterogeneous. This does go into the future, of course, as well. The latest predictions are to see a slight flattening. So rather than doubling the number of transistors every 2 years, it's going to double roughly every 3 years, but it's still increasing pretty fast. Almost business as usual for the next few years. That means we're going to have 20 to 30 billion transistors in a high-end chip in the not too distant future, which is just it's a mind-blowing amount. And what are we going to do with all of those transistors? Well, the belief is we're going to go more and more parallel and increasingly heterogeneous. And one of the other industry pundits who likes to watch his space is Herb Sutter, who was the person who coined the term "the free lunch is over," and he has a more recent prediction, which is that we're heading into increasing heterogeneous systems, and I've highlighted the last sentence of his quote here. A single compute-intensive application will need to harness different kinds of cores in immense numbers to get its job done. The free lunch is over now. Welcome to the hardware jungle. And the jungle is all about going heterogeneous and how much more complicated that makes all of our lives. So what are the causes of heterogeneity? We've now got multiple kinds of programmable core. And this is a big change from what we've been used to in the past. Not just the CPU, and there can be different flavors of CPU as well. You can have lightweight CPUs, heavyweight GPUs. A good example right now is the ARM big little type approach. But now we also have GPUs, we have DSPs, we have other accelerators, encryption blocks, we have video codecs, all on chip, all becoming increasingly programmable. And to get the most performance for your application, you need to harness all of those. We see asymmetry in the interconnect in a system on chip. We see memory hierarchies. They introduce a lot of heterogeneity, and software, of course, introduces heterogeneity in a system. So many causes of this, not just having a CPU and a GPU. I really spend a lot of my time doing high-performance computing these days, and we see a lot of heterogeneous systems in that space. I've picked out a few here. The Intel Mike, as was now the Xeon Phi. We've also seen AMD introduce a range of integrated processors that have multi-core x86 and fully programmable GPUs on the same chip. We've seen things like the Mont Blanc system, which is a project in Europe being led by the Barcelona Supercomputing Center, which is looking at integrating ARM plus GPU systems for HPC. And NVIDIA's been doing this kind of thing for a while, both in the embedded space, so with their Tegra line of processors, but also they're talking about what they're going to be doing at the really high end in Project Denver and things like that. So that's sort of where I come from, but even in the embedded space, of course, we all know that now everything is becoming heterogeneous. So we have a couple of examples here. The latest handheld Sony device has a quad-core ARM and an Imagination GPU in the same system, and pretty much all tablets and smartphones now are heterogeneous systems that are fully programmable. So this is becoming mainstream very rapidly. We may not have caught up yet and have all the software to exploit these, but the hardware is going this way very, very rapidly. There are a lot of limitations. This is all still very new. So here is what we face today as programmers that causes our lives to be complicated. We've got different memory spaces still. So we may have mashed a GPU and a CPU together, but right now they still have different memory spaces. The programming models have this hard notion of what's a host, what's in charge, and what are devices that you tell to execute kernels. And actually that's quite inflexible. There's quite a coarse-grained model of data parallelism. So when you want to fire up a kernel, there's quite a lot of overhead involved, and you need quite a lot of parallelism for it to be worthwhile getting the parallel beast going. And that's limited us to which applications are worth getting to run in parallel on these heterogeneous systems so far. Having very dynamically varying parallelism also is very difficult to support. So when we know how parallel a kernel needs to be, and it doesn't change, that's quite easy. But if, as we're running, we know we want to do a bit of this or a lot of this while doing a bit of something else, right now that's quite inefficient to support in current systems. Today we still have quite a lot of overhead in scheduling heterogeneous tasks and parallel tasks. Again, so we need to find quite big, chunky parallelism to make it worthwhile. And we know lots of real applications are much more fine-grained than that, much more finessed than that. And we haven't been able to support those efficiently yet. So these are the kinds of current limitations we see in things like OpenCL and CUDA that we've been trying to overcome. But, so these things are being addressed. They're fairly well understood what the limitations are. There are multiple ways people are looking at trying to address these limitations. And I'm going to talk about HSA, which is one of the emerging approaches to address these issues. It's not the only one, and who knows what will happen to HSA. It's a new proposal, a new standard that's emerging. But it is a very good example of the ways you can try and address these issues. So let's have a quick look. It is an open standard. It was proposed originally by AMD, who were doing something like this for their own purposes. But very rapidly, other vendors, especially IP vendors, said, this is a good idea, why don't we collaborate? And so far, the major HSA consortium partners are AMD, ARM, Imagination, and also some of the big consumers of IP, so Samsung, Qualcomm, etc., TI. You see lots of other names you recognize in there as well, down at the bottom with the STs and Tensilicas and things like that. And some academic groups are starting to get involved as well. My own group in Bristol is quite interested in exploring HSA, so our little logo's down there as well. So this is something you can get involved with if you're interested. It was launched really very recently, only last year, and it's an open architectural specification which includes HSA-IL, which is a virtual instruction set, a virtual parallel instruction set, in fact. Also includes a formal memory model and a dispatcher and runtime. And it's really being targeted at making things like OpenCL, C++ AMP, etc., render script, much more efficient. So you have more efficient implementations of all of these parallel programming models that we'd like to be able to use. Here's what it looks like at an architectural level. So at the top you have an application or a library. So it's mentioned Bolt in here, which is a library AMD has developed for doing lots of interesting parallel kernels. And then you'd have things like OpenCL or render script that would be sitting on top of a new HSA runtime, which itself has an intermediate representation which will eventually be running down on a GPU or a CPU. In many ways, this has a lot of similarity with OpenCL, which is no surprise because the idea here is that this can plug in underneath things like that and make them much more efficient. So we'll look at what each of these pieces does, so it should be more obvious what's going on. One of the first things is, one of the goals is to target a unified virtual address space and to make that possible for all the cores of the system. So this is something we don't have right now. But it does mean CPU and GPU will share a coherent virtual address space, This is very useful. It means you will be able to do things like pass pointers from a CPU to a GPU. You don't have to actually copy all of the data from one address space to another if you don't want to. That's going to enable much greater efficiencies. And it will enable PGAS-style distributed arrays. So that's partition global address space distributed arrays across multiple cores. This is something we're quite used to having in high-performance computing, but we don't have yet in these more embedded systems. Another thing that this should enable is having hardware queues per core. So right now you might have a hardware queue for an entire GPU, and that actually has quite a lot of overheads, and it's quite restrictive in what kind of models that supports. But hardware queues per core, and that's any kind of core, CPU or a GPU, gives you a lot more flexibility. I'll say what that enables a bit later on. But what it's really trying to give you is the ability to do things like context switching on the GPU, preemption. So imagine if your GPU in your phone is running the user interface and it's doing some image processing, you don't want the user interface to start going all slow and choppy because some computing that's running. You really want to support preemption and quality of service and things like that on the GPU. We don't have a way of doing that right now, but this is trying to get towards making that more possible and more efficient. And another issue, which sounds very kind of techie and very detailed, about barriers as objects, but actually one of the big challenges we have is when you have hierarchical parallelism, how can you write software in a way that you're not really sure what you're going to be calling or what's calling you? And what if the thing calling you was parallel, and you want to be parallel, and you want to call a library that might be parallel? That's really hard to coordinate. And one of the problems is when you have barriers as a way of synchronizing, usually those go right across a machine. And you really don't want that to happen when you have this kind of hierarchical, dynamically varying parallelism. So you really want barriers to become a first-class object which you can pass around and parameterize in some way. And this HSA architecture is really targeted at supporting that kind of feature so that you can have composable parallelism, libraries at different levels, all of which might be parallel. So we're going to drill into each of these components a little bit. First of all, the HSA-IL, the intermediate layer. Any of you who are familiar with OpenCL, and I should ask, so who in the room has actually used OpenCL or is wanting to use OpenCL? Okay, so quite a few people. What about things like RenderScript? Anyone been using RenderScript? Not quite so many. What about NVIDIA's CUDA? Any CUDA stuff out there as well? A few more. Okay, so most people have used one or the other of these. You're probably familiar with this idea of an intermediate layer. All of these things generally use LLVM as the compiler, and that has its own intermediate representation, LLVM-IR. OpenCL has had this project called SPIR, S-P-I-R. It's a standard portable intermediate representation. The idea is for this to be a bit like NVIDIA's PTX. It's a fairly standard high-level assembly language which can then be generated by lots of different OpenCLs, and then from this OpenCL SPIR representation, that can be finalized to a specific architecture. Well, HSA is going to do something very, very similar as well. It's a slightly lower level version than the OpenCL SPIR. The idea is that most of the optimization should have happened by the time you get to the HSA-IL. They're all based on LLVM-IR, so they'll all be very, very similar. And the idea is you can take something that's been turned into this intermediate representation and make a late decision about which core to run it on. And as you decide this is going to run on that GPU core or this will run on that CPU core, you can make a very lightweight last-minute assembly or a finalization, as it gets called, to turn it into the real instruction set for that specific core. And this gives us lots more flexibility about scheduling decisions, where to run specific tasks at runtime rather than at compile time. And HSA-IL includes things like support for calling printf and doing I/O and all of those useful things that we rely on. So that's HSA-IL. There's a memory model. It's been designed to support C++11, OpenCL, Java, all these things, Python. It's a very relaxed consistency model, uses load, acquire, store, release type semantics, designed to support both the unmanaged languages we all grew up with, like C, but also managed languages like Java. And the idea is to make it very easy to add more support into the ecosystem. So we can have more people producing compilers that target a standard intermediate representation, which then uses vendor-specific tools to finalize for a specific architecture. So this will be a good thing if it happens. And a dispatch, and this is for me, one of the kind of really interesting bits of HSA. The new architecture says have a work queue per core. Every kind of core has a work queue. You don't share a work queue for lots of different cores. We distribute work into queues, and we can load balance between cores, and we can load balance by doing things like work stealing. This is, again, very useful in a real heterogeneous runtime system where we want to do load balancing. Any core can schedule work. This is quite a big change. So now a GPU can create work for itself. Or a GPU can decide this is a piece of work that may be more efficiently run on a CPU and give that task to a CPU core. So rather than one host being in charge and deciding to farm out a task to a GPU or a CPU, now every core can be creating work or deciding the best place to run something. And this should enable much more efficient programs, much more finely distributed programs than we've been able to have today, and a big reduction in how much work there is when scheduling a task on a particular core. Actually, I'll skip over that one. So here's the kind of model that we've got today, which is we might have several different applications running. In this case, I've said maybe they're running Direct3D, but they could be OpenCL, something like that. We go through a whole bunch of different stages where the application makes a call to something like Direct3D. That then goes into a user mode driver, which puts things in command queues, which might have soft queues managing them. And eventually you go into a kernel mode, and then eventually there's a DMA buffer, which eventually writes something into a shared hardware queue. And there are lots and lots of stages with lots and lots of overhead going through the current model. And what we'd really like to get to is something that looks more like this, where lots of those layers have all gone away. We've got various cores at the bottom. Of course, the GPU can be broken up into multiple cores as well. There's one or more hardware queues, these ring buffers, per core. And on the left, we've got CPUs creating work for themselves. That's what we're used to. In the middle, we've got CPUs creating work for themselves or for the GPU. That's what we're used to as well. But now the GPU, of course, can create work for itself, which we can't really do right now, or back for the CPU as well. That's a new path that wasn't there before. And that gives us a lot more flexibility. While NVIDIA isn't doing something like HSA at the moment, they don't really need to. They don't really consume other people's IP so much. They are doing something very similarly with their own architectures, and they've got things like dynamic parallelism they've been talking about recently, which is doing very similar things. So this isn't really an HSA-specific evolution that we're talking about here. It's the way most people are going with their architectures. So here's something I stole specifically from AMD, which shows sort of where they've been going on this journey and how far they've got. But it's pretty interesting because most people are doing something very similar. And where we've got to recently is now we'll be able to support things like C++ a bit more, even with GPU computing, into the kind of user mode scheduling era in 2012. 2013, this year, we're starting to get unified address spaces between the CPU and GPU. That's going to make the programmer's life a lot easier. Starting to have pageable system memory shared by the CPU and the GPU. That's a big deal, because that means we can start passing pointers around rather than copying big chunks of data from one place to another. And having fully coherent memory between CPUs and GPUs. That's a big deal for the hardware guys to implement. I mean, it really is a big deal. That's something major they're doing on behalf of the user, but it does make the user's job a lot easier. And things still to come, but in the fairly near future, will be things like support for context switching, GPU graphics preemption, and quality of service. So this really is so that the user interface that might be running doesn't get trashed by trying to use a bit of GPU compute. Something we need for real-world embedded parallel applications. There is, if you're interested in this, there is actually a software stack that does this. that you can get hold of and play with. And in fact, my group's just got hold of this in the last week, so this is all fairly hot off the press news. AMD basically are releasing their software stack for you to play with. And all of these layers, apart from the last two, are general purpose. So it's only a finalizer and the kernel driver, which are specific to a particular vendor's hardware. All of the rest are vendor neutral. So if you're doing research and this sounds interesting, you'd like to get involved, you can get in touch with the HSA Foundation and say, I'd like to start playing with HSA, please, for research, and they'll give you access to this software stack. And the motivation is, this is a kind of parallel program that we'd really like to be able to support. And what we've got here is across the way is showing the width of parallelism at any one stage in this application, and down the way is time. And it's actually a trace from a game. And in this game, we're doing things like there's some graphics, there's rendering, there's some artificial intelligence, there's some game physics, all kinds of different things that are very different kinds of parallelism, and the exact amount of parallelism is unknown until you're about to do it. So it's a very dynamically nested parallel application. Doing this with sort of the existing versions of OpenCL and CUDA and all these sorts of things is very hard, but with the kinds of advances we've just been talking about, this kind of application is much more easy to support in an efficient manner. Efficient both in terms of compute and in terms of energy. So hopefully things are about to get a lot better for all of us users. So to conclude all of this, heterogeneity is a really important trend. It's really mainstream already in all of our mobile devices. Open standards are thankfully emerging and becoming really important, especially in the mobile space. In high-performance computing, we've got a little bit stuck, but in the mobile space, I think OpenCL and other things in that space, hopefully things like HSA, really taking off. The parallel programming models are still evolving. As we've been discussing, there are still lots of big limitations today, but the change is happening. And these HSA-like architectures, not just HSA, but what the other vendors are doing as well, should enable much more dynamically heterogeneous, nested parallel programming applications and models, which will be good news for all of us. So that's it. My group does quite a lot of work in this space. You can look us up and find out what we do. We do a lot with GPU programming in the UK. And as a last plug before I finish, we've recently created an OpenCL user group, and it's by users for users. It's called Comportability, which has a website. Just started, so there's not much there yet. If you'd like to be involved in some way, get in touch. And for that, we're also running an annual conference. We actually had the first one last week, which was at Georgia Tech in Atlanta. And we're planning on running the next one this time next year, and that one will be in Bristol, so it'll be much easier for most of you to get to if you're based here in the UK. And that's it. Thank you very much.